Okay, hello everybody. Welcome to EA Technology's second webinar in the series. Today we have both Stuart Ed to the left of me and myself, Gareth Devine, here to host and talk to you about PD and some of the examples we've found over the last 12-18 months. Myself, Gareth, I spoke to you the last webinar. My background is in electronic design and particularly test instruments and PD instruments for the last 15 years. Stuart?
I'm Stuart. I've worked for EA Technology for 17 years, mainly on the handheld, doing practical side, going out doing partial discharge surveys for in the UK and around the world.
So talking from two different angles really as we go through, so very much from the how to detect and then what does that mean, what does that mean to you on site, how would you follow up, and effectively how do you keep the lights on at the end of the day. So just a quick recap for those that didn't see the last webinar. It is available on our YouTube channel. There's a link towards the end of the presentation. But in that webinar, we covered the different detection techniques, how to very briefly use the equipment to actually detect PD. And we offered the follow-on of demonstrations, etc. on site. And we've seen a few of you since then. So thank you for getting in touch. Today's a deep dive into probably 7 or 8 different case studies of activity that's been found over the last 12-18 months, and to say looking into how it was detected, what there was there to see. So when you actually strip the kit apart, what would you have seen on site? And then in a couple of cases where action wasn't taken, how long did it actually take to fail? So you've got the full life story there. Just before we jump into that, a very short introduction to EA Technology for anyone that's new to us. So as a company, we've been around for well over 50 years now. Started Electricity Research Council and then migrated to the commercial entity of EA Technology through privatisation. We cover a wide range of activities from the PD elements we're talking about today through to consultancy and the training arms, and we're quite a worldwide coverage. Our customer base is general electricity distributors and the industrial application of it. Overall, you can sum up what we do is we help create safer, smarter networks, and in some way we help keep the lights on. So we do that in a number of ways. So our offerings cover a whole range of activity. This wheel kind of gives you a feel for it. So depending on where you are in your asset life cycle, we may be, as we are talking about today, helping with your field activity. So what's the state of my equipment right now? How do I keep it safe? Maybe through to, hopefully not, a couple of forensic investigations, it has gone wrong, right through to planning your next steps. So what investment should you put in going forward? What's the minimum amount of investment you'd require to keep this network reliable? And then on the other half, what's the policy, procedures, and the operating instructions are there. So kind of the consultancy and design stage as well. So a full breadth of network operations are covered by us at EA. And today we're focusing on the tactical PD element. Those who did join us on the last webinar, remember this slide coming up, which was about where does equipment fail? So showed this textbook example last time, which was highlighting overall that yes, PD occur, or failures can occur in multiple places. More often than not, they're in either moving portions or areas where people are involved, cable terminations, etc. The slide deck we've got today, you'll see, covers the whole area. Also covers a little bit on transformers. And you'll see samples that don't just cover the cable terminations or the circuit breakers, but also the fixed portions. So some really good case studies and a safety note probably coming up a bit later on the bus bar area and see the things we've seen there the last 12-18 months. So really, wherever it is in the gear, there's examples where it does fail, but statistically, these numbers hold true. So most risky parts where people are involved or things that move. Okay, so I'm going to start with a case study from Stuart, and I'll just hand over to him now.
Okay, so the first case study we're going to go into today is around internal partial discharge. It's probably one of them components that's actually got a lower percentage than some of the others in the end, but we'll say what we're going to go through is how we first identified it using the non-intrusive techniques, and then how we narrowed it down to the individual component, and at the end of the process. So this is the type a cross section of the same type of switch gear and a picture. And you just look on this picture here, we do show where we generally take transient earth voltage measurements. So the transient earth voltage primarily detects internal partial discharges, so it picks up the EM field that are detected to go into the switch gear, and we can detect it down on the outside using the capacitive coupler on the front of the device. So all we need to do is place the UltraTEV Plus on the front of the switch gear, flat against it, and it'll give us a reading. And we normally take it from these primary components, so the circuit breaker, cable box, CT chamber if it's separate, the VT on the top, any piece of steel really on the switch gear, probably the end of the buzz bars as well at either end, and whatever access we can get. So each individual piece of steel we should be going around and taking a measurement from. So in this case, we've done a switchboard, whole switchboard, and we found some elevated PD levels on one of the panels. This is the phase resolved partial discharge pattern. So what happened here is we detect each signal, and we use a frequency lock, and we can determine where on the sine wave we use the time to plot each individual event over 10 seconds. And over that time, we start to build up these things called the phase resolved partial discharge pattern. And that gives us extra information on both the type of PD, what phases it may be on, whether it's on multiple phases. So we can look at that plot and determine what we can get. So on this particular one, we can see that we've got a nice sort of leading edge here. It's classic for a void type discharge. Can you see that? Yeah. And then the second one on the right hand side here. So maybe two sources of internal void type discharge on this particular panel, or on the switchboard. What we did then is we narrowed it down using the time of flight, and we came to the panel itself and determined that we've definitely got partial discharge in this particular panel of the switchboard using time of flight. So the next step then is, because it's an internal discharge, it's not really very easy. It's not going to be visible. So with some of the discharge we talk about later, the next step may be to open it up and have a look. In this case, it's a bit more difficult with an internal void type discharge. So we could probably want to start splitting the circuit down, kind of still with non-intrusive detection methods. But what we can do is we can take a measurement after switching operations. So as in this example here, I've just put a line through the middle of the circuit breaker. So we've opened that circuit breaker. We also, the first step we did is we took the cable terminations off from the cable box, and we energized it, and it was still there. And then we opened the circuit breaker, and it went away. So in that case, we've come down to a couple of components really: the circuit side of the circuit breaker, and the CT and the bushings, and obviously the fixed portion of your spouts here. So now we've narrowed it down to that area using the non-intrusive detection techniques. After that point, you've sort of got to where you can really with non-intrusive, and the next step is to start doing an offline measurement and energizing each part of the switchgear individually and down to the component level to determine which of the components may have partial discharge. So the customer actually took a number of measurements and determined that they wanted to narrow this down much more. So we went to site with a 50 hertz power supply. So we've got a 50 hertz full frequency power supply, a couple of coupling capacitors, and a smoothing capacitor and a coupling capacitor, and then we can detect. So we did two tests. We did one where we just gone up through the spouts onto the circuit side. So we basically got the circuit spouts, the CT chamber, the CTs, and the CT bushings. And the second test that we did was the circuit breaker on its own. So we took the circuit breaker out of the switchboard and tested that to see if there's any partial discharge on each. The advantage of doing it offline, you can narrow it down now per phase as well. So you can do each phase individually. It's a single phase supply at that point. So this next slide shows us the results of that testing. So what we found is the circuit breaker was completely free from partial discharge. We never detected any activity at all on the circuit breaker itself and the circuit bushings. So we decided we would then look at take the CTs out themselves. So when we went up through the circuit bushings on the fixed portion side, we did detect partial discharge on L2 and L3. So at that point, we've determined, right, we've definitely got something on the circuit side, the circuit bushings, and we took the CTs out of the switchgear and tested those individually as well. So this is a picture here of the CTs in situ, and then we did take each one out individually and tested those. At that point, we can see, so this is the measurement screen that we can get, so we can see our little waveforms created by partial discharge, fast high frequency waveforms, voltage we're putting on, and then we can see the phase resolved partial discharge pattern on here as well. So on L2 we were seeing clear partial discharge up to about 9,000 PC, and then on L3 we again very clear PD pattern, very distinctively like partial discharge. We're expecting two clusters of activity 180 degrees apart, because that's where the voltage is rising, and we can pick up that partial discharge activity. And what we can see then is, by going back to our original online measurement, these two groups of activity indicate partial discharge, and we've picked that up and we've split that down, so we can now, the customer's replaced those two CTs, and the activity has gone away on that particular panel. So we've just got the next slide just shows a few examples of these types of things that we have found in the past. So obviously you've got to do a laboratory forensic investigation to cut these in half, but once you've cut them through, you can see things like these internal voids, CTs. This is one that has actually failed, and this is one that was detected prior to failure. Okay, thank you.
Thanks, Stuart. So I think that shows initially, just by using a handheld device on the outside of the switchgear, you get a very clear picture of what's going on. You could see from the initial measurements the two different sources. So you knew, if you actually started to act on that and cleared one of them, the second one would have still been there. And the lab test has followed that up and have the same patterns. So to give you some reassurance, you get a lot of questions in this work about how can you do this on the outside of the switchgear. And I think that just demonstrates the fact that we can. So moving on to the next section, PD and transformers, completely different topic. More and more of these around now, especially on single sites. So one of the places we're going to talk about in a minute is more data center application. There's hundreds of these sort of transformers in those sort of locations. But transformers come in all different shapes and sizes, or friendly oil filled transformers, or these more cast resin type or a dry type transformer. So let's start with the oil filled transformer ones we know very well. So first thing I'd say, we're talking a lot about PD measurements and about how we use our handheld equipment or permanent monitoring to detect. On an oil filled transformer, possibly wouldn't start there. One of the first things to mention is DGA, dissolved gas analysis. The condition of the oil within the transformer will give you a lot of information about what's going on. Taking a sample of that oil and getting that tested in the lab is a relatively inexpensive process to go through. It'll let you trend the age of the oil and the degradation of the transformer over time very well, and will give you, plenty of time and headroom and some service options in terms of replacing the oil, etc., refreshing the oil, which allow you to extend the lifetime of it. So if you're not doing DGA analysis, it's worth looking into. It's also worth looking at how you do your analysis. So the actual process of removing the sample, the method we use is a sort of a dual valve method. A lot of these transformers have been sat there a while, and we don't particularly want to just rely on the transformer drain valve. Once you open that, we want to make sure we can close that flow off. So we use that dual valve approach. There's a couple of things to consider, but slight segue, but if you're not doing DGA, very much worth looking into and considering. So where would you look for PD? Nice and simple on a full transformer. Most things from a PD point of view call back to the cables. And we're able to therefore take measurements on the cable itself and on the cable termination. So the cable box on the outside metalwork using the TEV, so that contact transient earth voltage capacitive sensor in the top of the device. Additionally, for the air-filled cable boxes, we want to try and get an air path in there to see if there's any termination activity, any surface activity. Quite often these are vents that are kind of on the base up around by the bottom of the cable, where you can get a clear air path in. Or in the case of a sealed box, we look to use our contact probe, which allows us to pick up the ultrasonic activity, so that's surface type discharge, through the skin of the metalwork. So not a preferred option, there's obviously an attenuation path in that, but as you'll see in a minute, it does work, and you can see inside that sealed box. So moving on to example, and this is a slightly challenging example. So this is a contact probe being used on the outside of the switchgear. This is actually on the cable box, and you can see I'm just going to play an audio file for this. There's two things you look at when you're using ultrasonic sensors. One is the data, so some of the classifications in there, and the other is the audio file. The audio files normally have a very clear pattern to them. I'll just play this one for a second. So it's the first one of our demonstration, and it's the least clear, hopefully, you're going to hear today. So the audio file for this isn't particularly clear, but there are signs in the phase plot that this looks like PD. There's this clustering going on, and there's our classification there. So, question to yourselves, with that information in front of you, would you be thinking of taking an outage? There's a quick poll, I believe, it's been pushed out on that. Okay, so what are our thoughts? Actually missed a slide there, you've just seen the answer. That's okay. So what are our thoughts? So would you take an outage? So our initial advice was yes. Why were we confident to do so? From the audio file, that there's quite a lot of 50 hertz hum going on in there. The normal crackling, arcing, and sparking you'd hope to hear isn't as clear as you'd like. Our confidence was built mainly through two pieces of information. One is having a phase reference. So we've used, in this case, our wireless phase reference, which allows us to transmit a phase lock to the handheld device, however you are on site. And that lets us see where PD activity is happening on the phase, and gives us this plot in the middle. That has a very typical 180-degree separation build-up of PD activity, plus some shapes in the initial build-up that makes you think that is surface activity. And then there's a lot of AI and algorithms we built into the device that now classify that automatically. And that classification is presented as PD or noise and a confidence factor. And you can probably see on the screen here, that left-hand red circle, the device gives a high confidence that this is PD. So when we were able to advise a client that, yes, this outage should be taken, despite a phone call partway through saying, do we really want to do this? Because one of the bolts has just snapped and it's all very shiny on the outside of this gear. We had the confidence to continue, and internally this is what was found. So this isn't the same transformer as in the example picture at the beginning, but you can see the metal work to the left of that first picture. It's well painted, it's well maintained. From the outside of this, you wouldn't have had any visual indication of any issue. Taking the lid off, following the measurement, you're able to see that there's been a lot of deterioration. Probably started around the cable clutch. That's then created an acidic atmosphere inside the cable box, and now the cable boots and everything are all deteriorating with a high amount of rust, etc. So definitely a good find, and something you would have wanted to act upon. And all being all, a relatively easy fix as well at that point, is re-terminating those cables. So conclusions from that one: reliance on the audio file alone, you could have overlooked it. You would have heard there's some activity there, but you may have just put that down to noise. Don't let it detract from the fact you should always use a headphone. You should always be listening for this, because the fact there's a difference in the first place is why you look deeper. So that's quite important. But then once you pause, you let that plot build up, you use the phase reference, we'll then be able to give it a good classification and act upon the output of that. So that was the easy one, the oil type transformers. Dry type transformers, slightly different kettle of fish. So dry type transformers, there's a lot more places where we can take measurements. Cable box, cable, still very valid. A lot of stuff comes back from there, especially internal type discharges. And we'll be able to pick that up on the cable sheath, or again on the surface of the cable box. But generally, you've got a lot better access. There's air vents right round, but there's also a lot more open connections, a lot more dust, etc., collecting in there. Lots of other failure modes that creep into these transformers that are more likely to give you surface activity that we can detect ultrasonically. So you're taking measurements in a lot more locations. You also, from an ultrasonic point of view, do have to have the challenge of 50 hertz hum, the natural hum and load variations of a transformer. So that's something to be wary of. So moving on to the next slide, I'm going to play a quick audio file. Let's see what you think on this one, PD or noise. Okay, so this particular one is common across this particular site. You'll find this on 60-70% of the transformers across there. It is background noise. A couple of clues. One, okay, let's take the easy route. The classifier is telling us that. The AI that's built into there is saying this is noise, don't worry. But you've also got very tight vertical clusters or clusters and 1.5 cycle. It's not typical of PD. So the phase patterns, you start to learn them, will give you some extra confidence, some indication that's not PD. The audio file as well, very repetitive, most of tone to it. There's none of this randomness you'd expect from a PD activity. Conversely, looking at another measurement from the same type of transformer, you can press play on this one. Probably hear that arcing and sparking. So with PD, the physics around the PD discharge site will change with every cycle. So you won't get an exact repetition. It'll be a slightly different amplitude discharge, a slightly different part of the cycle each time it occurs. And that gives you that nice arcing, crackling sort of noise you can hear there. Effectively, it's a spark we're listening to. You'll also notice the pattern here. So it's only 1.5 cycle, a very significant level discharge. This, I think, see on the screen, we're probably on that 30 dB, 25, 30 dB, which is a significant level discharge. So again, do you act and when do you act? So this is one of those cases where PD was detected, but the time planned for the follow-up was left a bit too long. In this case, actually failed within 4 months. So it was our first round of measurements on this site. So unfortunately, we can't show what would have been 12 months ago. But from detecting activity of that sort of magnitude and repetition rate on that type of transformer, we've then seen a failure within 4 months. So planning your actions and importantly, surveying regularly enough to give yourself time to act is key. And bear in mind that surface activity will generally tend to failure a lot quicker than any internal void or internal activity. So in general, you should be reacting quicker to surface activity. So just a couple of slides there on transformers, but to highlight sort of things you can find, how simple it is to take the measurement still, and just that importance of planning your next step.
Okay, so now I've got another couple of case studies on bus bars, which is another section that was mentioned at the start as not very often having partial discharge in because they don't move much. They're put in on day one and they should be all fine. But we have seen a couple of cases of those in the last 12 months or 18 months. So in this case here, this is the first time we've been to this site. They'd purchased an UltraTEV Plus 2 and wanted a benchmark survey for us to go around, do a full site survey and give them the results so they could carry on doing the surveys themselves going forward. So it worked out as a really good example for them to listen to partial discharge activity, which is always helpful when you're doing training. So in this case, we have a bus bar, sort of a main bus bar joggle box. We're just listening around the air gaps. There's no clear air gap. There's no holes, no bolts missing, but just around literally the seam across the back of the bus bar chamber, we could hear this discharge. So I'll just play this for you. And again, we can see clearly that the phase resolve plot, it's a bit round. You've got to imagine the phase plot goes right round the circle in this case, but so you can see part of it on one side and the other side. But we can quite clearly hear that it's definitely ultrasonic activity, but it's very, very small gap. So it's not necessarily easy. We can get sound through very small gaps. So I can imagine inside it'd be much louder. So we did also use the contact probe on the same box. On the same box. I'll just play that for you so it's quite clear. Again, we've got good strong phase resolved pattern on there, and we can hear that sound really clearly. So again, we're thinking, it's quite in my experience that was quite a severe partial discharge, so we did recommend that the customer opens it up as soon as he can. I think they did within a few weeks, and they did send some pictures over, which is always nice to get that feedback from the customer afterwards. And we can see inside there's a lot of sort of gaps. So where all the bus bar supports are there, we've got these little gaps around where the bus bars are going through. And these do create a lot of electrical stress in those areas. So because it's a little air gap, different dielectric strength to the material that's holding it, it does actually cause partial discharge activity by increasing the stress across that area. So you get little discharges across all these little gaps. And what that does is it starts to create this acidic atmosphere, similar to what we mentioned earlier. So we can see any of the bolts within there, the nuts and bolts that are all rusting away. And we see little damage to all the supporting structure. As you can see, it's quite an aged switch gear. It's been in for many years, but it's starting to fail now. And you see other ones. So this verdigris, this greening again, is caused by the nitric acid on the copper work within there. And then the little air gaps, we see little white bits and damage around there as well. So the customer had it all stripped out, and he filled in all the air gaps. So we can see here, this is after it had been rectified by a local contractor. So you can see we've made sure now that there's no little air gaps going through any of these voids. We've insulated everything, so that should lead to a much longer life for that area. It's a bit of a funny box, jogger box arrangement. So there is probably originally there was probably a bit of slightly different components put in than would normally be. Okay, and then the next one is a surface activity on VMX switchgear, but not necessarily in the normal area we would expect around the circuit breaker, and that we did find it in the bus bars on this occasion as well. But this does highlight that we don't always get transient earth voltages when we've got severe, quite extensive ultrasonic or surface related activity. So there are two totally independent tests, so we should always be doing a transient earth voltage test and an ultrasonic test to make sure that we can cover both types of partial discharge, both internal and just surface and corona type discharges. So this this layout here is out of the software, so we can see each of these symbols, how well you can clearly see them, but they indicate a TEV measurement, and they're all green. A couple of ambers at the end, probably a battery charger at the end of the substation. But in here we can see the red ones, and we can hear this sound coming out of the cable box, the VT chamber, and also in the circuit breaker. On the next slide, I've got the sound file from the circuit breaker. So on this type of equipment, we would normally have a good listen right around the circuit breaker itself. So you got the spouts at the top, we can get good line of sight into there. And we can listen in there. In this case, the loudest point was just up at the left, but it was going inside. So I'll just play the sound for that as well. Quite a loud one. It'll woke you all up anyway, if nothing else. And we can clearly hear the partial discharge activity. But just to reference back to transient earth voltages, so transient earth voltages across the board were pretty level, around 10 dB. No real, so as we've seen a lot of phase plots that are quite classic partial discharge. So they've got the two groups, 180 degrees apart, things like that. In this case, we've got a plot that's completely flat right across the sine wave. So it's unlikely to be partial discharge related due to, we've got some areas of this which would have 0 volts. So at that point, but obviously we have got a pretty strong partial discharge source within that board still. So there again, they carried out a visual inspection of the switchgear, and this is up in the bus bar area, just above where the bus bars actually come through from the top of the circuit breaker and connect onto the main bus bars. And you can see extensive surface tracking, lots and lots of verdigris and rusting of components. Again, probably not that long. It's probably been initiated originally by probably high humidity in the substation. So if you've got this type of equipment, any air insulated switchgear really in a high humid environment, you will start to get partial discharge activity. It will increase it, reduces the dielectric strength of your air. You start getting dew points on it and things like that. So that leads us into another case study where we're talking about the effects of humidity. Well, Gareth's going to talk about the effects of humidity.
Thanks, Chip. It's quite topical, man. Anyone in the UK, unfortunately, probably suffered the storm last week, and quite a few areas were flooded. So humidity in the substation might be a permanent thing. It might be something it's there for the nature where the site's situated, etc. But it can also be a very temporary thing, something that comes through flooding, and the damage is caused. The PD starts at that point, the deterioration starts. You're happy your site's dried out, everything goes back to normal, but that deterioration continues over time. So if you have had any sites that have had flood damage, would recommend just considering that, following up on what the impact of that might be, and have you checked going forward. Okay, so a couple of slides just on the effects of humidity. This is just by way of a case study, really. So this particular one, 33 kV bus belts where the issue was. And so it's an audible discharge head in the substation. So you don't need any fancy kit on this one. You could walk in, you could hear discharge going on. It's that sort of level already. The humidity in the substation, so this wasn't the UK example, it was over 95% humidity at the time. And the signals were located to the circuit breaker chamber, but difficult to localize, because quite often when you've got very, very high levels, it does become challenging to see, okay, well, that one a bit quieter than this piece. So trying to use direction microphones, etc., becomes very, very helpful at that point. In terms of what is detected, so with the +2, the ultrasonic was at 36 dB. Now we care when things go above 0, really. We really care by the time it's 6. So at 36, just give you a few orders of magnitude away. That's significant. And the TEV was also showing it is surface type activity. It's 11-ish pulses per cycle. It's in the right sort of repetition rate. And there's probably more than one phase of PD involved looking at that pattern. So fairly clear, yes, we've got a problem. And as you can see there, we can hear it everywhere, even looking through the LV compartment to the compartment just behind that, you can see it coming through. So any small gap, really clear. With our monitoring system, you can see here that activity was very much related to humidity. So we weren't fixing it by controlling humidity, but in terms of buying time, in terms of slowing the progression, putting dehumidifiers in there and lowering the humidity, it's still not quite getting to a level we'd like. It's still 60 odd, 65%. We want to be close to the 55 probably. But from the 90, 89 to you're at, significant drop, and a significant drop in the level of activity. So controlling humidity, heading down to the 55 mark, will make a massive difference to how often that activity is sparking, how quickly it's degrading, and the likelihood of it starting. And that's shown there on the trend of the two graphs. So what was it? This is enabling because the customer sent through a fantastic video, which I'm going to show you on the next page and give you a feel for what PD really is. So this is showing the actual corrosion of the connections here, and this is through environmental conditions, what's caused that tracking on the spouts. The next page is this taken offline and energized from a low energy source and recorded from a safe distance, and you'll see here just what the arcing looks like. You should see marking and sparking and going on there. Just on the surface of the insulation there, that's starting to arc away, and each one of those sparks is doing a little bit of damage. So it's some energy release that's eating away at that insulation. And if you could zoom in on that, you'd start to see a treeing effect. And that treeing effect is why you get a much higher number of pulse per cycle, number of events per cycle, and you get an internal discharge. You've got multiple discharge points going on at any one time. And that's heading towards that earth points and events to a flashover. So a couple of messages in there. Surface activity in general, stop it happening by keeping things clean and control the humidity. If you have got it going on and you have got high humidity, before you rush out and do anything else, control the humidity, monitor the activity. You can bring that down, buy yourself some time if nothing else. And post flooding, just consider that's something that's becoming more and more topical. We're seeing a lot of questions around these days, unfortunately. Okay, now on to one of our favourite topics of the year. So, empty cubicles. Let's walk past them, I think.
Okay, so yeah, empty cubicles. So in a lot of substations, there'll be a lineup of 10 panels, and there might be one or two of them that aren't actually being used at this present moment in time. And we've seen, I've heard of 4 cases this year where we've either detected partial discharge on those very early, before failure, or they failed this year. So just something to remind you that you don't just, if it's an empty cubicle, don't just walk past it and survey the next one. It's very important to double check that. So in this case, I've got a couple of example pictures. So this is a vertical racking switchgear type. So you've got you've obviously your 6 bushings there, and your 6 spouts. So you can, one side will be connected to the bus bars, and the other side will be going to the circuits. In that case, you've still got your 11 kV, your 33 kV, just a few inches away from this piece of earthed steel right in front of it, and the same on a horizontal type here. And the ones I've heard of have both been of either type, vertical or horizontal. And again, the humidity can affect that. If you've got high humidity, I think one of them was associated with the heaters not being on in the panel as well. So if you've got a bit of humidity and you've got this, relatively short distance between the two, you can quite easily get a flashover between there, and you start getting partial discharge activity. So if you've got some panels in your switch room and the breakers racked down, but these are there, definitely always have a listen round with your ultrasonic microphone as a minimum, and take some tab off the breaker still, even though it's not physically connected, just to make sure there's nothing major going on there. So I've got a couple of examples and a couple of and a picture on the next slide. So this was one that we detected in service. So is switchgear panel, switchgear lineup, VMX panel, and all the other ones were running, and this one had its breaker racked down. But literally just put your microphone into that little area and we could hear it clear as day. And it's actually on the circuit side, and you can listen to that sample as well. This thing is relatively loud. So they did arrange an outage. The customer actually arranged an outage on this one the same day, and they opened it up and had this beautiful picture of what partial discharge can create. You can see the tracking coming down the side, and this blew in, and it's all down to the really bad environment that really ends up in there because of this partial discharge activity. And you can see that it's probably been developing over time. And again, the humidity was quite high in this particular substation at the time of test, and it had been for a while, which is, I think it was taken out because the circuit was taken out because of that in the first place. So we've just gone to and then on the next slide, so we've got this one where we found it, detected using ultrasonic, and then this is an example of a picture of one that's gone to failure, and obviously no one would want to be in front of that. It does bring home what can happen when these things do fail properly. We're all stood in front of these all the time doing these surveys. So if you're ever going to operate switchgear, or you're ever around them, then make sure you've done a thorough PD survey of your assets.
Yeah, especially about to back into unused cubicle, that side of things. It takes 2 minutes to have a quick check for ultrasonic activity, and could make a big difference. So no way doing.
Okay. Go to our final one.
Okay, thank you. Yeah, so this is the final example, and I've squoze it in here a little bit. I'm just going to, before I go on to it, reflect on the couple of points. We put a poll in the chat before, would you took an outage or not? 50-50 response on that. I think I asked it now, having seen the pictures of the failure, it probably changed slightly. So, looking at and be able to trust the data off the instrument is a key part. And our aim as a business and our kit is to basically design equipment that gives you that confidence and makes that decision simple. I've concentrated today, and with it being an initial webinar, on a lot of traditional techniques, so TEV and ultrasonic. There are other techniques we cover. I'm going to bring one into the conversation in a second, together with some of the new noise immunity type stuff that we are doing. We will on future webinars cover UHF and all the whole host of wider techniques for other applications. But for now, I'm going to stick with switchgear, like cloud switchgear, and move on to the final example. So, solar farms, our favourite places, loads of noise, loads of inverters, generally built reasonably quickly to a budget, and they can be varied in quality and install everything else. We do see a lot of PD activities on solar farms, and in this particular instance was no different. There was high levels of PD measured with TEV right across the board. Now, I'll say PD, for that particular set of readings, it's not 100% obvious. So on this screen, you're looking at the phase plot, which you've been used to seeing on the base. You're looking at a view of what the waveforms, so for every dot on that screen, we've got example waveforms captured there showing, okay, what do these actually look like? And you can see one of those in the top right-hand corner. And then the left-hand graph starts to look at some properties of that waveform and brings a few things in behind the scenes. So from the TEV readings, we look at that going, okay, there's something going on. It's everywhere, not 100% clear. It looks to be PD. There's some very strong flat lines across the top of some sort of contact noise, but its location isn't particularly clear. We've then gone around and taken measurements to our VPIS device. So I introduced this in the last webinar, but this is a device plugged into the side of the plus, looks a bit like a cable with some electronics halfway, and that allows us to connect to the voltage, the VDS or the VPIS sockets on the front of your switchgear, and they provide a capacitive connection to the cable termination. So no longer are we trying to see secondary from the outside of the gear, we've kind of got a connection to the cable and to the bus bar now to see the activity. So this finds a much better location. So if you looked along the panels, we now know this is on this FDR4 feeder, really well localized. We can see here there are bits of this that look like PD, but the waveform would not give you any confidence of that. A lot of these waveforms are noise. You've got a lot of background noise going on. What we can now do with our tool sets or our service teams that we'll be using in the background is we can filter that noise. We can look at what the energy and the waveforms look like in certain parts of that activity. So going back to that question in the survey, would you take an outage? This allows us going from, okay, there's something going on, so there's something going on that's on that panel, and we've got confidence that does look like PD, not some other external noise. So that story is getting stronger and stronger all the time, even from handheld equipment. These sort of techniques have existed on some permanent monitoring systems, high-end ones for a while, but we've built, one of the world's first to get this into the handheld instruments and really about to bring this feature to you for our services. So what do we actually find? So it's not just data. When you move on to the next page, what you'll see is lightning arresters. So give you an idea where part of the world this came from with the terminology, that lightning arresters were loose and able to move freely on the back of these T-boots, which is never a good thing. In this instance, the particular bolt that was holding those on, you can see this pushing bolt has kind of started to eat away, and there's damage around the boot itself. Root cause for this, dead simple. Bolts are different sizes, different lengths. So the one phase that was tight, two phases weren't, one phase that was tight had a slightly shorter bolt than the other two. The other two were sticking out a bit too far. So from day one, a build error, the wrong component being used, and you've now got something that would have led to failure had it been detected. So there's a case study there of how the techniques and the analysis are starting to help give you the confidence in these decisions. And being blunt, that's what we're there for. We're not there to go around every site and take every measurement. The tool set's there for yourselves to do that, pushing them out. We're there to support the complicated ones. If you have questions, you have data sets that don't make sense, please get in touch. We will come and do PD surveys on site, of course, but we aim to skill you up to that level and help out where needed. So please always get in touch if you've got some readings you don't understand. Keeps my work interesting, if nothing else. Yeah. So that's the last case study. There is a quick Christmas challenge for you. So spot the PD. So nice cable termination. You'll see evidence of PD activity on the outside of that. jot down a number next to yourselves, have a quick look. How many different sources of PD can you see? There's a few, so I'll let you count. Okay, well, full marks for anybody. They got 14, and they're the visible ones from this angle. So there is activity starting there around the strain relief in the cables where the stretch relief is. You've got some contamination on the boots themselves. There's some stuff on the bushings at the back. There's phase identification tape been left on. That's always a one that causes a change in stress and, again, a breakdown of PD. All very early, all stuff that can be addressed, but plenty of bits of activity on there. And thanks to our colleagues in the States for sending that through. That was quite an interesting picture. Lots to see going on there. Okay, so from ourselves, a couple of those things. Wanted to extend our offer to book a demonstration. So we want to come and see you. We want to show off our kit. We want to come and show how we can help you on site, not just in PD, but in the wider asset management area as well. So if you'd like to come and demonstrate anything, talk through anything with our engineers, please do just get in touch. There's a QR code there, just to take you through to the booking page. In terms of what's next, this is a second one in our series, and there will be another one picking up in February, looking more at the management of the data. And finally, any questions that have come through? So looking now as a question. So.
One from Harish just come in. Is there a way to equip equipment with online or offline monitoring, real-time monitoring or periodic testing?
Okay, thank you. So not sure if you heard that. So there's one question come in, which is there a way to equip equipment with online permanent monitoring? Yeah. Okay, so there is, and thank you for the question. So we do provide ourselves permanent monitoring systems that can either be permanent or semi-permanent. So if you know you've got an issue and you want to trend that or manage that gear, then we can insert it temporarily. This just magnetic clamps to the outside of the switch gear, so it can be done with the system fully live, and we'll cover your cables, your switch gear and your transformers. Equally, that can be a permanent monitoring system with all the data back to the cloud, and we can manage that service for you. So yeah, definitely something that can be offered. Generally, obviously, compared to a handheld device, it's got a slightly higher cost, and you'll be using that in your more critical assets.
Thank you. Got one more coming from Wesley. Where are you seeing UltraTEV with the most adoption and best understanding? So that's geography and/or industry.
Okay, hi Wesley. So interesting. So where we see in UltraTEV the best adoption and the best understanding is really mixed. So in the UK, the DNO area, for instance, has got a long pedigree with PD. There is a user group that meet regular year with ourselves, and they have some really deep understanding of some of the failure modes there. Our biggest growth area there is probably the areas that haven't had much electrification before now. Electric cars, etc., vans, particularly fleet vans popping up all over the place. There's people now maintaining electrical assets that didn't have previously, and they've got less electrical capability on site in a lot of these cases. So UltraTEV really concentrates on making the user case simple and allowing through the managed survey offering, and which is the central web management of the data, advising what data to collect on each site. We really guide people through that collection. We're seeing a big uptake in that sort of area. And obviously, as you've seen from the case studies today, renewables are probably the biggest growth in terms of failures. Okay, well, that's the end of the questions. If there are any follow-up questions, please drop me an email. Myself or Stuart would be happy to catch up with yourselves. So thank you very much for joining. And as all that's left is to wish you a Merry Christmas and catch up with you all in the new year. Thank you very much.